Welcome to this explainer. Look, today we're jumping straight into what I think is absolutely the strangest mystery in all of physics, and we're going to unpack exactly how it built the modern technological world around us. It is a topic that fundamentally shifts how we view reality itself, and the findings are they're absolutely fascinating.
I mean, just look at this question on the slide for a second. Why on Earth can electrons just breeze right through solid barriers? And why does light act like a continuous wave but also like a solid particle? These massive paradoxes of the quantum realm literally kept the brightest scientific minds of the 20th century awake at night. But as you'll see, solving these bizarre riddles wasn't just some neat academic exercise. It became the literal foundation for everything from the smartphone in your pocket to advanced medical imaging.
So here is our roadmap to guide us through this quantum chaos. First, the fall of classical physics. Then, the birth of quantum theory, the wave-particle paradox, uncertainty and probability, the magic of quantum tunneling, and finally, powering the modern world. Let's get right into it.
Section 1. The Fall of Classical Physics. Okay, so as scientists developed better and better tools to observe energy and matter at the microscopic level, classical math literally just fell apart. It completely broke down. I mean, if classical physics were actually correct, atomic stability wouldn't even exist. Electrons would just spiral right into the nucleus, and atoms would instantly collapse. We also saw massive anomalies popping up, things like the photoelectric effect and blackbody radiation problems that led to the disastrous ultraviolet catastrophe. That was a mathematical nightmare where classical formulas predicted an object in thermal equilibrium would emit an infinite amount of radiation. Obviously, that wasn't happening in reality, right? We'd all be cooked. The universe desperately needed a new set of rules.
Section 2. Birth of Quantum Theory.
It's honestly awe-inspiring how rapidly these next breakthroughs cascaded. They unraveled centuries of classical physics in just a few short years. It all kicks off with Max Planck. He solved that pesky ultraviolet catastrophe by proposing something totally radical. Energy isn't a continuous flowing wave. Instead, it's released in tiny, discrete chunks, which he called quanta. That's energy quantization. Then, Albert Einstein took that a massive step further with his photon concept, proving that light itself was actually made up of these individual quantum packets. And building on that momentum, Niels Bohr developed his revolutionary atomic model. He showed that electrons exist in specific, quantized orbits around a nucleus, rather than just floating freely wherever they want.
Section 3. The wave-particle paradox.
Now, we reach the point where the plot really thickens. This highlights the ultimate paradox: light behaving simultaneously as a continuous wave and as discrete, bullet-like particles. For generations, scientists argued fiercely over which one it was, but the breathtaking conclusion was that it's intrinsically both. And here is where it gets downright spooky. This duality isn't just restricted to light. Through electron diffraction, we learned that physical, solid particles can behave like waves. It's a mind-bending reality mapped out by the de Broglie wavelength. Discovering this duality in solid matter was the skeleton key that unlocked our modern understanding of the subatomic world.
To truly wrap our heads around this wave-particle duality, let's break down the famous double-slit experiment. In step 1, if you fire particles through a single slit in a barrier, they hit the screen behind it in a single band, exactly like you'd expect solid objects to do. Simple enough? But in step 2, if you add a second slit, those exact same solid particles start creating an interference pattern on the back screen. That is a behavior completely unique to overlapping waves. They are somehow acting like a wave and interfering with themselves. But the most mind-bending piece, the part that still gives physicists headaches, is step 3. The mere act of observing it actually changes the result. If scientists place a detector at the slits just to see exactly which hole the particle goes through, the interference pattern completely disappears. It reverts back to acting like a standard solid particle. The universe literally changes its behavior just because we measured it.
Section 4. Uncertainty and Probability. So how do we make sense of a reality that literally changes when you look at it? Well, the crucial point is Heisenberg's uncertainty principle. This proves that achieving a perfect measurement of a particle's position and momentum at the exact same time is fundamentally impossible. And to be clear, it's not because our microscopes or detectors aren't powerful enough. No, it is a strict, hard-coded rule baked right into the fabric of the universe. The more precisely you try to pin down exactly where a particle is, the less you can possibly know about how fast it's moving and where it's going next. It is an inherent, inescapable blurriness to reality. To ground this bizarre concept, we can visualize Schrödinger's wave function. Because we can't pinpoint an exact location and speed, we have to rely entirely on probability. Instead of an electron circling a nucleus on a neat little track like a tiny planet, it exists as this fuzzy, three-dimensional cloud of maybe. It's technically everywhere in that cloud all at once. It only snaps into a definite physical location when an observation or measurement is made, triggering what we call the wave function collapse.
Section 5. The magic of quantum tunneling.
Let's transition from abstract math to reality and look at barrier penetration. This is exactly what happens when you treat matter as a wave of probability. If an electron is just a probability cloud, there's actually a tiny mathematical chance that part of its cloud exists on the other side of an impenetrable solid wall. And sometimes, it just randomly pops through. This is quantum tunneling. Fun fact for you, because you are made of particles, there is a legitimate mathematical probability that you could quantum tunnel through a solid wall. Actually, scratch that. You'd have to lean against it for a few trillion years to actually pull it off, but the math says it's possible. On a cosmic scale, though, it happens constantly. It's exactly what drives the nuclear fusion powering our sun. Without quantum tunneling, the sun literally wouldn't have enough energy to ignite. We've even harnessed this magic here on Earth. It's what makes scanning tunneling microscopes possible, allowing scientists to visually map the surface of materials atom by individual atom.
Section 6. Powering the modern world.
But why does this matter to you and the gadget sitting on your desk right now? Well, our ultimate mastery over this quantum chaos directly birthed the modern technological era. Once we finally understood wave-particle duality and the bizarre behavior of electrons, we learned to control them. This gave us semiconductors, which are the microscopic brains powering every smartphone, laptop, and digital device on Earth. Quantum physics gave us the lasers that scan our groceries, the MRI machines that save lives in hospitals, the LEDs lighting our homes, and the solar cells capturing renewable energy. Literally, none of these exist without quantum theory. And the evolution is far from over. We're now using these very same probability laws to build quantum computers, an upcoming technological leap that will process data in seconds that would take our absolute best current supercomputers thousands of years to figure out. It's a real game changer.
We've seen how the fall of classical physics gave birth to a quantum revolution that quite literally built the modern world. But I want to leave you with this provocative thought to cap off our explainer. If things are already this bizarre, what happens when we explore the future of tech with quantum entanglement? What happens when two particles link up and instantly communicate across the entire universe, completely defying the speed of light? It is the next great frontier, and a mystery that will undoubtedly reshape our world yet again. Keep questioning and keep exploring.